The heavy water reactor will use about 0.7% of the uranium's energy value, and the light water reactor will use about half of 1%. They both do terrible.
At normal pressures, water will boil at 100 degrees Celsius. This isn't nearly hot enough to generate electricity effectively. So water-cooled reactors have to run at over 70 atmospheres of pressure. You have to build a water-cooled reactor as a pressure vessel.
The number one accident people worry about, pressure is lost. Water that's being held 300 Celsius flashes to steam. Its volume increases roughly by a factor of 1,000.
If you don't get emergency coolant to the fuel in the reactor, it can overheat and melt.
This is what drives the design of this building. So if this happens, all the steam is captured in this building.
Now, the reactors we have today use uranium oxide as a fuel. It's a ceramic material, chemically stable, but not very good at transferring heat. If you lose pressure, you lose your water, and soon your fuel will melt down and release the radioactive fission products within it.
So they have a series of emergency systems
designed to always keep the core covered with water. We saw the failure of this at Fukushima Daiichi. They had multiple backup diesel generators, and each one probably had a very high probability of turning on. The tsunami came and knocked them all out. People sometimes say, is nuclear energy safe? And the first thing I say is, well, which one? Thousands of different ways to do nuclear energy. Is the car safe? Well, which one?
I had the good fortune to learn about a different form of nuclear power.
The liquid fluoride thorium reactor.
We can fully burn up the thorium in this reactor versus only burning up part of the uranium in a typical light water reactor.
It's not based on water cooling, and it doesn't use solid fuel. It's based on fluoride salts as a nuclear fuel. You have to heat them up to about 400 degrees Celsius to get them to melt, but that's actually perfect for trying to generate power in a nuclear reactor. Here's the real magic. They don't have to operate at high pressure. They don't have to use water for coolant, and there's nothing in the reactor that's going to make a big change in density. Unlike the solid fuels that can melt down if you stop cooling them, these liquid fluoride fuels are already melted. In normal operation, you have a little piece of frozen salt that you've kept frozen by blowing cool gas over the outside of the pipe. If there's an emergency and you lose all the power to your nuclear power plant, the little blower stops blowing, the frozen plug of salt melts, and the liquid fluoride fuel inside the reactor drains out of the vessel, through the line, and into another tank called a drain tank. In water-cooled reactors, you generally have to provide power to the plant to keep the water circulating and to prevent a meltdown. But if you lose power to the lifter, it shuts itself down all by itself without human intervention.
A staggeringly impressive level of safety, even if there's physical damage to the reactor.
Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. We could use thorium about 200 times more efficiently than we're using uranium now. Because the lifter is capable of almost completely releasing the energy in thorium, this reduces the waste generated over uranium by factors of hundreds and by factors of millions over fossil fuels. We're still going to need liquid fuels for vehicles and machinery, but we could generate these liquid fuels from the carbon dioxide in the atmosphere and from water, much like nature does. We could generate hydrogen by splitting water and combining it with carbon harvested from CO2 in the atmosphere, making fuels like methanol, ammonia, and dimethyl ether, which could be a direct replacement for diesel fuels. Imagine carbon-neutral gasoline and diesel, sustainable and self-produced.
You can see that uranium-235 is like on par with silver and platinum. Can you imagine burning platinum for energy? And that's what we're doing with our nuclear energy sources today. We're burning this extremely rare stuff, and we're not burning thorium. Some people who are kind of environmentalists, and they say, listen, nuclear power is not sustainable. We're going to run out of uranium. Okay, I will yield that point to you if we're talking about today's nuclear technology.
In 2007, we used 5 billion tons of coal, 31 billion barrels of oil, and 5 trillion cubic meters of natural gas, along with 65,000 tons of uranium to produce the world's energy.
So I have a friend who's trying to start a rare earth mine in Missouri. Jim, how much thorium do you think you'll be pulling up a year? He goes, I think about 5,000 tons. 5,000 tons of thorium would supply the planet with all of its energy for a year. And he goes, and there's like a zillion other places on Earth that are just like my mine. It's a nice mine, but it's not unique. It's not like this is the one place on Earth where this is found. Every time mankind has been able to access a new source of energy, it has led to profound societal implications. Human beings have had slaves for thousands and thousands of years. And when we learned how to make carbon our slave instead of other human beings, we started to learn how to be able to be civilized people. Thorium has 1,000,000 times the energy density of a carbon-hydrogen bond. What could that mean for human civilization? Because we're not going to run out of this stuff. We will never run out. It is simply too common.